the lithographic process works. So you've got that wafer that I showed you pictures of the wafer with the circuit on it. Well, this is the wafer of silicon. It's made out of silicon, and it doesn't have anything on it yet, okay? So the way the process works is you have what's called a resist, and it's a photoactive type of material. So you have a mask that goes over that. Now the mask is in the shape or the pattern that you're going to have the circuit in. So the mask is basically the shape of the circuit, what the circuit will look like. And again, it's very tiny, very intricate. And that mask is put over top of the resist, and light is shown through the gaps, which cures this resist in those areas where the light showed through. So now the area that's not covered with resist anymore can be covered with deposited material so that the circuit can be made. So basically that deposited material then, because the resist is preventing it from attaching in those areas where the light got exposed to the resist, those areas now, this deposited material can't set on, and that metal then is forming the circuit in all those locations. Okay? Then the resist that's been cured is taken off, and now you have a wafer with these circuits on it. Okay? Again, we're looking at a cross-sectional view. If you flip it this way, you'd see that wafer with the circuits that I showed you earlier. Now the way this worked originally, they have an alignment system, and it's again a very small scale here, very fine. You've got this alignment system that holds the mask in place. Okay, as it comes down, it holds it in place. Well, what happens is because that mask is in contact with the resist material, you can see up here in this picture, the mask is actually in contact with the resist. So it end up getting, the mask gets damaged very easily in that process. So that's very expensive to replace the mask and all those things. And so the architectural innovation that came up was to set an alignment system whereby the mask would actually not touch the wafer. So the light would shine through here, and the light would come through, and actually the light would disperse a little bit when it reached the edge of the mask. So you maybe wouldn't get as much precision with the process. So maybe now, instead of 10 microns, you have 9.5 microns of precision. So your precision isn't as good with that process. But what they found was because they kept things out of contact with each other, it would last longer, and they wouldn't damage materials, and so productivity would increase. Okay, so they could actually get more throughput in the system by having this different alignment system that actually didn't make actual physical contact. So we call that a proximity alignment. And then they had a number of other architectural type innovations. And when I say, again, architectural, we're not really changing the basic process here. It's still, you've got the mask, you shine light through it, you cures things. The process is still essentially the same. It's this alignment system that's modified over time. So the technology really hasn't changed. It's how we apply and implement that technology, how we arrange the technology. And this is, again, more focused on process, but there are other examples in product as well. So this is a summary table right here that talks about the different types of aligners. So you got proximity aligner, then this scanning projection, first generation stepper. So these are different approaches to producing the same type of wafer. So again, the technology really hasn't changed. It's how we're organizing it. And you see what happened here. This is a list of different companies. We start with contact lithography that I showed you first, where they're touching each other, then proximity. And what happened to this company, Cobuilt? 44% of the market, down to 8, or actually to 0, and they just disappeared. So they, had the majority of the market when you had this type of architecture. When you switched architecture, even though they invested in the equipment, They didn't have the core competency to work with that equipment, and they went away. So then you got Canon takes over. So you go to this proximity type alignment system, Canon takes the market. Then what happens? You go to scanners. Perkin-Elmer takes the market. Go to steppers, you got a new market entrant. And then step and repeat, Nikon takes the market. You see how the architectural innovation, even though these companies invest in the technologies, like Dr. Wabi mentioned about Kodak, they developed digital photography. Where are they now? That's what happened to these companies. Any questions on architectural? Again, I just want you to understand the concept. I don't want to turn you into stereolithography people unless you really want to do that. I suppose somebody does. Somebody has to want to do it, right? Okay. Questions on architectural. So we got radical, huge technological change, revolutionizes the market, architectural innovations, and the last type, and probably in many ways the most important, incremental innovation. Or in the manufacturing world, you might hear the term Kaizen, if you haven't heard that before. Continuous improvement, essentially, is what that means. Incremental improvement. And basically, you're building on existing knowledge. You're improving the current state of knowledge in that technology. Good example of that is with computers. I understand you're supposed to be talking about computers in the world this week or something. So this fits right in. You look at computers over the last 10 years. Have there been any major changes in the technology? Processing speeds improved. The storage capacity, RAM, so you can open up more files and more complicated software. But really the core root idea of the computer hasn't changed much over the last 10, 20 years. Maybe more. I'm getting older. Maybe it's over 20 now. So that's a good example of incremental innovation. What else? Anybody got any other thoughts on incremental? Can you think of one in incremental innovation?
Cars?
Okay, what about what's incremental innovation?
Well, I mean, they just kind of get a little bit different, a little bit better.
Gas mileage?
You know, right,
Gas
exactly.
mileage is, they've made vehicles that are better gas mileage. There's an example.
Safety side.
Safety, airbags, okay. I got a whole nother discussion on those things, but, well, I'm going to sidetrack a little bit and get all away from my planned lecture. But, you look at these new technologies, and what do you see? What have you seen happen over the last 10 years with the new technology that comes out? Like interlock brake systems. Who remembers when they first came out with those? Anybody? I'm older, see? I don't mean to say that in a mean way, just more experienced. Interlock brakes, what company came out with them first?
I have no idea.
Most of those innovations like that, you see come out on the real high-end vehicles at first, don't you? And they're real expensive, and this is the thing that separates us from the competition. Well, we got analog brakes now. And if you remember the analog brakes when they first came out, it was gung, 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 real slow repetition. Now they're like, they really work well. But when they first came out, it was a big deal. Oh, this has analog brakes, but it's the $50,000 vehicles that have them. And now every car pretty much has them, okay? So what happens is, in the beginning, that new technology is a differentiator. It separates you from the pack. And then over time, now you got to come up with a new differentiator. Something new that you do differently than the other competition to separate out and say, this is why you should pay $60,000 for our vehicle, because we have this technology. So over time, those technologies diminish and become the norm. That's what you find happening. Kind of a sidetrack. But anyway, I'm going to focus a little bit on incremental innovation. I'm running longer than I expected, so I'll try to zip through this. Again, I'm not expecting you to know remember this stuff long term necessarily, unless you're interested in it. But if you look at manufacturing performance, we look at things like speed, quality, dependability, cost, flexibility, and how do we improve those things over time? Let me just go to, so we look at some different improvement methods. Plan, do, check, act. It's more of a management cycle. So you plan something out, you do it, you check and see how it did, what improvements can be made, and then you act and make improvements, and you go through the cycle again. So it's kind of a cyclical way of thinking about continual improvement. And again, it can be applied in just about everything you do. Another one is the 5 why process. So give me a problem that you have. Anybody? Who has a problem? Who has a problem they want to share with me?
Technological problem?
Anybody? Wow.
All problems are
High
solved.
class. Give me a problem you're having, Dr. Wabi. Don't be shy.
Well, a technological problem, maybe the internet being slower sometimes.
Okay, the internet's slow. Why?
Why?
Why is the internet slow?
Well, that's a good question.
So it's a root cause method. Let me give you an example we can walk through. Okay, my back hurts.
Why?
Oh, I'm glad you asked. Well, my back hurts because I haven't been exercising.
Why?
Why? Well, I don't have time to exercise because it's not a priority. Oh, well, now we're getting closer to the root cause. So you kind of see how the process works? So it's a way of, being deliberate about trying to find what the real cause of the issue is. You can start to begin to address it, because until you get, drilled down to that root cause, it's hard to solve the problem. It's like putting a Band-Aid on, something where the Band-Aid isn't going to be effective. There's a deeper issue. Okay, I'll skip over that. We'll go to the next slide. So I'll talk briefly about some tools of problem solving, and then we'll wrap things up. So these are some different, again, tools that are used for incremental innovation, solving issues day to day, to try to make things better, improve processes, improve operations, and so forth. So these are some different tools that you may find useful for that type of activity. So I'm going to talk briefly about each of those. A check sheet is just a tally sheet. If you want to find out, this is looking at traffic. How did people find out about something? Did they look at newspapers, daily ads, weekly ads, websites, road signs, or referrals? How did they find out about something? So you track that and tally it up. 7 people on this day, 4 on this day, and so forth. So it's just a simple check sheet, a way to tally information so that you can look at it then, and very quickly you can see what's the best approach to use. There's a couple that are much higher than the others. What are they? What are the most effective ways that they're getting information out to customers?
Website.
Yeah, the website and daily newspaper ads. And you can flip that upside down and create what's called a histogram. That's another tool. And it's basically taking those counts and, spreading them out. Where did the most occur? And looking how that spreads over time. So like you could take a measurement of something you're producing and, measure that device. Let's say you're measuring the width of something, and somewhere it's supposed to be about 1 inch, and you're measuring it, and you get various measurements. So maybe this is exactly 1 inch, and then these are spread out from that. So 1.1 inches over here, 0.9 inch, and so forth. Just an example. So you're taking counts and you're plotting that data, and you're trying to see how much variability there is in something. So you've got a measurement. How much spread is there in that measurement? Are you between 0.9 and 1.1 inches? Are you between 0.99 and 1.01? How fine is that? How tight is that measurement? How precise? And how accurate? If this most common measurement is 2 inches and you're shooting for 1, what does that tell you? Really far off, right? So that's the histogram. Again, it's just a quick method plot data and see what you've got. Another way to do root cause analysis, if you're trying to identify, let's say I've got a process operation and I'm making something and I'm getting defective parts, defective product. And I track over time and see, which things in that product have issues. Are they fasteners, connections, interface and protection, the main part, structural components, labels? Where am I having defects occur? And so I can count that up, I can track it with the Pareto chart, and essentially I'm just counting up the number of times that defect appeared when I made my product. And you might have some products that have multiple things, so you count them in multiple columns. Another way to do that, rather than counting up the number of failures, if you look here, look at structural down here. I only had 24 structural failures, so it's not a big issue, right? I shouldn't worry about that. What should I worry about according to this chart? What's my biggest concern? That's where I'm going to get the best bang for the buck. If I address the fasteners and get that right, boy, I've cut way back on the number of defects, haven't I? But you can also look at that from a cost perspective. How much did those 24 structural defects cost me? Oh, whoa, whoa. Hold on, now I've got a flipped issue, okay? Before, what was the connectors? Fasteners, right? Fasteners was number one, now where's it at? It really doesn't cost me much money to have that kind of defect. So I'm not going to be concerned about that. I'm going to address the one that's costing me the most. If I can fix those 24 structural defects, I can cut my cost of failed components down in half. Okay? So that's the Pareto chart. It's another tool that we use for continuous improvement. If you have any questions on these, if I'm going too fast, I'm not trying to turn you into experts necessarily. I'm just trying to give you some tools that are out there. If you want to look more into these, they're very easy to find on the web. So you can find out more detail about them and practice using them, integrate them into papers that you're writing. Now the next one's scatter diagram. And this is just looking at relationship between two variables like temperature and viscosity of a liquid. Might be one example. So is there a positive correlation? When one goes up, the other goes up too? And is it linear? When this doubles also? So that's a positive linear relationship. It's a very strong one because you don't see a lot of scatter. Okay, we're over here, you have a moderate positive relationship, and we say that's moderate because it's not really, if you fit a straight line through that data, you're going to have a lot of points that are further away from that line. Whereas over here, fit a straight line through that data, most of the points are going to be pretty close to that line. So moderate positive relationship. If you look at the relationship here, you got data scattered all over the place. There's not really any correlation between the two. So when one goes up, the other might go up or it might go down, you just don't know. So there's no relationship between the two variables. You can have a negative relationship, and again, moderate or strong, depending on the scatter. And then another possibility might be there's not, maybe in the beginning when one's going up, this is going down, and then at some point it hits a tipping point, and it actually starts increasing as the other increases. So getting an idea of how two variables are related can help you to solve problems. Let's say you've got a machine with multiple settings on it. You've got a setting for pressure, temperature, humidity, those three, let's say. And now you want to see how those three variables relate to each other. Again, knowing how they relate can help you to get the right settings to produce a product. So that's where the scatter diagram, looking at relationships of variables, can come into play in a manufacturing or production type setting. Process flow charts, if you're trying to look at a process and see how it's operating, this is used a lot in computer programming. It's also used in manufacturing. And what you're trying to do here is identify how you can make the process move more smoothly, trying to eliminate waste in a process. That's where the process flow charts are used. The next one is a root cause analysis approach. I shared one with you earlier. What was it? Root cause, what did we do? My back hurting, 5Y, okay. This is called the Ishikawa diagram. It's also called the cause and effect diagram. It's also called the fishbone diagram, and it basically looks like this. Let me draw a picture over here. This is a horrible pen. How many good pens? Where's a good pen? Oh, that's much better. So the reason it's called a fishbone diagram is because it kind of looks like a fishbone. So you've got some problem here on the right. Okay, again, Ishikawa, cause and effect, and fishbone diagram are all the same thing, just different words that are used for it. So you're essentially trying to identify the root cause of this problem. So you identify major areas, okay, and you can see those here for this particular case, and that's not locked in, those can vary by the problem. But you identify main areas, and then you identify sub-areas within those. So, you know, maybe you don't have the right people in the company. Maybe you need to hire some new help. Maybe your management is disorganized or they treat people bad. So there could be issues that way. Maybe the equipment's old. So you're identifying potential problems, and then through this you line up, find out, okay, what's causing the problem, and then the group that has the most knowledge about the process of the people and the problem, the organization, looks at that and figures out what are the main areas that we need to fix to try to correct this problem. So it's again a systematic way of drilling down and finding out what the root causes are. The last one, just a run diagram. That's to try to see how a process or something is done over time. Maybe it's a measurement, maybe it's, again, trying to see, you know, in this particular example, you've got a registration time at a doctor's office. So you're looking at the amount of time it takes versus the day. So some days it's performing well, some days it's not performing well. Some days it takes a long time to register patients. Okay? So this is just one example. Again, it could be a variable, a measurement that you track over time. So you randomly take a shaft that you're producing and you measure it. And you take that measurement and then you plot it over time. And you're seeing how that variable is performing. You're looking for lots of scatter, you're looking for trends. You know, let's say you've got a shaft that you're producing and the diameter keeps going up slowly, but it's creeping up over time. What might that be something? What might that indicate? If your diameter, you're trying to produce a 1-inch diameter shaft and over time it just keeps creeping up. Maybe it's 1.1 after a month. What does that mean? What might be causing that?
Dye might be getting worn or
The
something.
dye worn, tool wear, yeah, very good. So again, getting an idea of what a variable is doing over time, how you're performing over time. You know, if you've got certain days where certain staff are in here on these days when you're not performing as well, maybe there's some retraining that you need to do. You know, to help those people to perform better. Intermix them with the people that are performing well so you get some cross-training to happen and bring those highs down so you're performing more consistently. So again, a way to help identify the issues and solve problems. So those are just some tools, again, used for incremental innovation. So what did we talk about? We talked about 3 types of innovation. Radical innovation, what's the example of that? DVDs from VHS. Kodak we talked about.
Yeah.
Architectural innovation.
Semiconductor.
We talked about the lithography process. You're not really changing the core technology, just reconfiguring some things in that process to make it improve. And sometimes we saw the data, companies get left behind in that process, don't they? Again, trying to adapt your core competencies as a company so that you can work well with the new innovations. And then finally, the incremental innovation, continuous improvement, trying to improve over time. And here you see those S-curves. New technology, incremental innovation, radical innovation. Or it could be architectural too. Okay? Questions on the S-curve? So, in closing, be open-minded, be a continuous learner. Those are important things. That's what we hope people get out of college, and they become continuous learners. They don't stop learning. I sure hope I don't. I don't think I have. And this finished files is a good example for you to remember that. Silly thing, but makes a strong point. Any questions?
Any questions?
You did very well.
I appreciate the opportunity to come and talk to you.
That's very well.
If you ever need anything, downstairs,
Room 1010.
1018 actually is my room, but yeah, in the office complex down there. If you need anything, let me know.
You say your name was again?
Austin Cheney. Cheney.
Chair of the School of Technology. Because when we arrived at the first unit of aviation. Okay, so please join with me in thanking Dr. Cheney.
Thank you. I appreciate that.